I have a wonderful electronic invention I want you to see. It looks something like this.
Welcome to the very first chapter. This will be a fairly short one, but it will set the tone and give you an idea of what is to come. I let the chilled guy take it from here and just annoy you from time to time.
Thank you. In this very first section, we want to set up the foundation of the whole system, and that is the terrain as a basis for the environment and the curve that will become the rail. I want the system to be fairly flexible, which means it should be able to create its own terrain and curve, but also be able to switch to an incoming terrain from outside of the project. So let's start setting this up for that. We need an object node that I called the Railsystem, because that's exactly what it is. The whole system will be contained in this one node.
All of it. Are you f***ing nuts? This will be a nightmare.
Relax. Hear me out. Right at the start, I create a null to be my control node. The whole system will be controllable by the parameters on this node. This course is organized in multiple chapters for easy reference. I'm going to combine all parameters in folders according to the chapter where they are first introduced. For example, once this project is finished, it will be quite heavy to be processed. So right at the start I want to build in a safeguard, a toggle that must be checked for the system to start processing. I also might need a global seed that can manipulate the output of the system. And with that, we have our first parameter. I'm going to try and make this node tree as clean and easy to maintain as possible. The approach of building a giant node tree in one container may sound scary and chaotic at first, but the overall concept grew on me. Let me know what you think about it, and what's your first impression of it. But I can already promise you, you will see some benefits later on during the project.
You better hope so, otherwise that dislike button will be smashed faster than you can say banana cake.
So let's begin with the terrain this system can create on its own. Even though I'm aiming for a mesh terrain in the end, we start with the height field nodes of Houdini. These are a brilliant tool set to create any terrain of any kind. But even though I'm aiming to get a fairly detailed terrain out of this project, I will only roughly touch on it and focus on the procedural chain in which we use it. But still we need to make use of the basics. Let's start with the basic height field node. This default 1000 by 1000 field can be seen as the canvas to basically paint the terrain that we would like. And in my case, I'm actually going to paint a mask that will be the base. So how does that work? You create a height field paint node and paint away. What you create by doing that is a mask which can tell the system where you want to do something. The more color you apply, the more you want to do it, especially in that area.
So, is there any way to read that in a non-suggestive way?
I don't think so. So what do we want to do? We want to add some form of detail to the height field. The easiest way to do that is by adding noise. By default, the noise is applied in the whole height field, but when you connect the mask to the second input, the node knows where to apply it. To get even more detailed, a good way is to combine different noises of different element sizes and amplitudes. In combination, these noises will help to break up the repeated patterns that one single noise would create. And finally, by adding distortion on top of it all, you start to get a good-looking base. Terrain generation in Houdini goes a lot further, but that is all we need to look at for now. Since the idea and purpose of this series is generating complex geometry that adapts to the terrain, I prepared a result that will demonstrate the different features, but the process is exactly what I just showed. You paint a mask, add noise and distortion. And that is basically all we need to get the system going. Let's add a bit more. The key tool for terrain in Houdini. The height field erosion node is basically a compact simulation that is applied to the height field to simulate natural processes. This will start to give the terrain the look and feel of a real landscape. Again, there's a lot to this node, but it is not the focus of this series. Just understand that this is a solver, which I can freeze to do a certain amount of work. For example, 15 frames of simulation, and then freeze it in that state. When you go to the Visualization tab, you can also start to apply colors. Just compute the range. And the default scheme gives you a good feeling for the terrain you get out of it. A good idea to stop the system from simulating the erosion is by creating a time shift node right behind it and set it to that frame, where you also froze the simulation. It just takes out a bit of the hassle that you sometimes get when working on larger projects, where you have a lot of different chains working together.
Oh yeah, I remember last time when I had a project like that. It was a clusterfuck.
I went back and deactivated the colors, since they will come in at a later stage. For now, let's add one more height field node for more details, and that is the slump node. This will create the impression of debris running down and gather at the bottom. And once again, a lot that can be done here, but I just want to show you that the tools are there, while adding something interesting to the height field. Now, at this point, we could make use of our trigger parameter on the control node. The creation of the terrain does already involve some processing, and maybe we want that to happen only if we are ready. An easy way to apply a trigger like that to your node tree is by adding a switch at the end of it, maybe even the switch if node. Let's grab the parameter for reference, and while the test type set to expression, paste it to the enable parameter. If the toggle parameter is active, it sends the switch node the value 1, which in turn means, yes, this path is enabled. The node is set to use the second input once all conditions are true.
You are just trying to be fancy.
Back to staying clean while creating this node tree. A good way to do that is select all nodes that belong together. Press down the A key and slide it up or down to vertically align the nodes. In addition to that, we can add a node box with a name. Let's do a quick check. The toggle now does what it should. Just to be clear, the toggle is just an idea how to control your project and stop it from doing all the processing. That can give you better performance while you work in other areas. It is not a critical setting to the system, but what is quite necessary to keep the project clean is that you apply your own rule set of naming and coloring notes in general, but especially if you give this one container layout a try. Having only one container does not mean you will have wires run around everywhere, connecting hundreds of nodes. Each logical unit will have another null to mark its output. For myself, I'm going to use a bright green for these outputs. For the namespace, I just started with the chapter number and a matching name. You could be even more precise and add another number to note which step this was. For example, write chapter number _ step number _ name of the null. This would make it even easier to organize it later, but I think we can get away with being able to see all chapter outputs when searching for the right one. You will see what I mean later.
Seriously, the suspense is killing me. I can't take it.
Now to the second part of the foundation, the curve. Even though it will play a crucial role, you can be fairly sloppy with this. Just draw a curve from one point outside of the terrain over to another one, making some turns for more interesting behavior. Even though any roughly placed curve will work, it has a very strong impact on the result. So I also prepared a curve that I want to use. This curve on this terrain will urge the system to do a lot of testing, find possible options, and create the geometry accordingly. Now that we have the terrain and curve in place that the system can generate on its own, we need an example for terrain and curve that comes from the outside. It is a question on how you want to go about it, but since at this point, I have still a height field, I do expect the external input terrain to be 1 as well. Making it possible to process a mesh is easily done also. I give you a pointer where you would do that. For now, let's just create a fully random terrain, just for demonstration purposes. We do the same thing, height field, multiple noises, output at the end. And we also create another container for the example curve. The same way as before, we draw a rough path across the terrain without much regard to the amount of points we use. The only restriction, I would say, is not to create too sharp of a direction change. It would still work, but it would also not look very good when the train goes through it.
Exactly. Hold on to your pants while sitting in a train making a 90-degree turn. Fun times.
Now back to our control node. To make use of the external input and determine which one is to be used, we need to operator path parameters. They will point to the geo-container where the external input comes from. We also need another toggle to make the choice. Let's finish these new parameters, and then hit accept. I want to bring in the possible external terrain and curve, so open the Choose Operator dialog, and connect our examples. Besides the output nulls, there's another node type that should receive its own color, and those are the object merge nodes. I will use a bright blue throughout the project, even though everything will be inside this container, and could be connected directly. We can use the object merge node to point at any node without building a wire chaos. With this first merge, we go about it like you're probably familiar with it. We point at the external terrain outside of this container. While with another merge, we grab the terrain from within the Railsystem. There's no difference between connecting a node directly or by going through a merge node. But you will see that this allows us to keep the tree fairly tidy. And at least from my view, it is easy to jump around.
Maybe you should plan out your project in the first place. Then you wouldn't need to jump around as much. Fruit cup.
So both terrains now get connected to a switch node, which will have a reference to the trigger that activates the use of the external inputs. As you can see, the flag is not active, but currently we see the external terrain anyway. For the switch, it is crucial to have the right order. The toggle sends a 0 or 1, which in turn activates the first or the second input. Keep in mind that unlike the switch-if node, the normal switch can also get values beyond 0 and 1 to activate whatever more inputs you connected. So you could, for testing purposes, create a lot of different terrains to test the rail behavior, but remember that you would need a different parameter rather than a toggle to control it. Now we do the same for the curves. Bring in the external and the internal curve outputs, and then connect them to a switch, using the same toggle as a trigger. Whatever comes out of these switch nodes is the foundation to the rest of the system. During the project, I'm going to make it a habit to isolate each logical step in a small unit of the node tree. That way it will hopefully stay very readable and becomes a good learning project. Let's check the toggle again. Without processing, there is no internal terrain. Using the external inputs now shows the external curve and terrain. So that works like it should.
Okay, I get it. When are you going to the good stuff?
So we have a selected terrain and a selected curve, but again, you might want to prevent the system to start doing all of that work at the moment. So as a last example of that, we could create a new switch-if node again and put them in before the output nulls. Set up the reference to the toggle parameter, and as we saw before with the default settings, the active part would go into the second input, while the toggle is inactive. The input should come from the first input. That input in this case is just doing nothing. This is not just helpful to prevent whole sections from being processed, but you could also use it to lighten the project during iteration. For example, instead of stopping the terrain creation altogether, we could also use a toggle called Use Detailed Terrain to create different branches where the erosion and maybe the slump nodes are not active. That way you would always get a basic version of the system, but bypass what makes it heavy to be processed. And these toggles could then be used in the current take, one for lower and one for higher quality. But let's go back to the task at hand. Whatever height field was selected at this point now gets converted into polygons. I do that because I want to do Boolean operations with it later on. I also want to do some collision testing, utilizing geometry functions like intersect.
So that's when I would throw in a polyterrain.
Exactly. Now let's clean up this section. Create an out null, Chapter 1, Initial Polyterrain. This was one capsuled step in the process, so again I grab all of them, and they get their own node box. I call it Select Input. And that brings me to the last step I'm going to cover in this small first chapter. I want to limit the amount of geometry that is used for some of the operations later on. To do that, I'm going to split the terrain into what is close to the area of interest and where the rail will be, and the rest of the terrain. For that, we obviously need to bring in the initial poly terrain and the curve, whichever was selected before. Now the very first step is to smooth the curve to be somewhat more usable. So use a resample node to get a lot more points on it. And by turning it to subdivision curves, we get smooth turns as well. But at this point we don't care too much about the curve, but the terrain near it. To test if it is near, I'm going to connect the curve into a point wrangle that will apply a small piece of vex to each point. I want to test if at any point on my curve, there's terrain below it, and if so, where exactly that is. I'm using the intersect function for that, which works similar to the Railsystem.
And if you are still wondering why he doesn't use the Railsystem then, you have not listened before. That dude is a coder. That's what he does.
But don't worry, I will also try my best to stay reasonable with that. When a SOP node makes more sense, I go with that.
But it is your Cody brain that decides what makes sense, so that calmed no one.
What I want to do is shoot a test ray straight down from the curve, but that only makes sense if the curve is above the terrain. I don't want to bring that burden to the user, so I push the points way up. How much is determined by a channel that I call terrain test lift. I'm going to need to vector variables for the intersect. The function returns the primitive number that it hits, and so I catch that in a variable called PR. Quick reminder on functions. The very first parameter of almost all functions target the input to be used, starting with 0. In my case, the terrain is connected to the second input, so I use 1 for this parameter. The origin for the ray is the position, and the direction goes straight down, let's say for 2,000 units. Whatever is definitely enough for your terrain. If the intersect does not hit a primitive, it will return -1, so we can test that with an if condition. If that's the case, we are beyond the terrain where we can clip the curve. Points can be removed using ptnum for the current point. If it's not -1, so else to the prior condition, the function overwrote the variable pos with the position where the hit occurred. The channel for the lift is still initial. Where that was not enough to be above the terrain, the points are deleted even inside of the field's area. The curve is then connected at the next point, where it emerges again. The idea of separating the terrain mesh could also work to ignore the areas, which are way above what will be the rail. But I do want to do some additional work on the terrain, so I want to have the whole slice to do that. I push the lift high enough to stick the curve, even on the highest mountain. This parameter again should be on the control node, and referenced in the wrangle. I'm showing you a few times how I create the parameters and connect them in the project to the control node. But in the future, I'm going to spare you from this. The idea is that all critical parameters that do something in the system are on the controller. And here is another rule I'm going to use to help making the node tree easier to maintain. As I mentioned, I'm going to use quite a number of wrangles. A wrangle, however, can hold a simple line of code to make a simple test, like we have done here, but it could also hold critical logic to control the whole system. To make it easier to see which wrangles are nodes of importance, I'm going to color code all wrangles from a light yellow to a deep red, according to its complexity. It is just my own gut feeling what that means, but it still helps to quickly find those important nodes in the system. We will need this curve again, so let's create another output, now using the naming and coloring convention. and then we can prepare the terrain split. This time, the terrain is in the first input, and the surface curve is going into the second. In my book, this will actually do something to the system, so I make it a stronger yellow. I think you get the idea. This time, it's not a point wrangle, but a primitive wrangle. That means we iterate over all prims, rather than the points. I made the choice because I want to add and set an attribute on the primitive. It just saves some loop iterations, since there are less prims than points. At this point in time, I can share my past ignorance with you, so you can learn from my false thinking, and maybe it clears up something for you as well. Some of these Vex snippets I wrote ages ago, when I first set up the project. And here and there, I made errors. But rather than writing it differently from the start, and to avoid those problems altogether, when it makes sense, I keep it in there, to give you the pointer into the right direction.
So listen to this. For the longest time, this dude thought that the attribute P, the position that is saved on the points, he thought he needs to address the points to get the position. Who doesn't know that you can use it P on a primitive wrangle anyway? That will give you the center of the primitive. What a moron!
This only goes for the built-in attributes though. It is the same way the other way around. You could use the attribute primnum in a point wrangle. It would give you the primitive the point belongs to. So what I'm about to do is still valid, if you would need a different custom attribute. So I need a point on the current prim. To get that I am using the primPoints function, with the current prim number.
Remember, the moron could have just used the attribute at ptnum. Would have been the same f***ing thing.
I just want to use 1 point on the prim, since I don't need to be overly precise here. Depending on the terrain's resolution, the difference between the individual points can be ignored. So the function returns an array with all points on the prim, and I pick just the first one. Then I grab its position with the point function. Again, this could be any other attribute as well, but since here it is a position, I can now get the distance between the prim point and the closest point on the curve. That can be provided by using the minpos function. If that distance is bigger than a certain threshold, then it gets an attribute called remove, which is set to 1. All other prims never reach this branch, but still get the attribute, by default set to 0. Altogether, we want to tell the primitives that are too far away to be removed. I set that threshold to a value of 30. And as you can see in the spreadsheet, there's a good number of prims, now with the remove attribute. Since it now can only be the one or the other, a good node to use is the split node. I want the main output to be all the primitives that do not have the remove attribute set to 1. So a type exclamation mark equals 1. To make it perfectly clear what comes out of this split, I create new output nulls for the initial partial terrain and one for the rest of the terrain. Of course, these are parameters that should go into the control node, giving you the option to change how big the slice of the terrain should be. Again, this step had two purposes. For one, I showed you a first little glimpse into applying Vex to solve tasks, or problems. And on the other hand, we can now limit future work in the system to the slice of the terrain that is actually relevant. For example, to place the rail towers and bridges. And with that, we can already wrap this first chapter. As you can see here, this was only a fraction of the whole system. But I felt this was the first logical unit that could be capsuled in a chapter. I hope you found this interesting. And we'll be back for the second chapter, where we take a closer look at the rail itself.
Yeah, you better come back, or I will roundhouse kick you in the throat. Now that we have some time together, why don't you click that subscribe button? You know you want to. You will forever regret it otherwise. Do it. Do it now.